about electronegativity and bond polarity. And these are important because they're going to help us predict how molecules act in particular situations, right? Really going to give us an understanding of materials. So let's start out. Now, the electronegativity we're going to define electronegativity on the next page, the next slide. But first of all, I'm going to point out to you that in your text, you've got a nice little graphic which gives you electronegativity measures, which I haven't defined yet, on particular atoms, right? So the electronegativity of fluorine is 4, gallium is 1.6, barium is 0.9, and so on, right? So this is a figure from your textbook. This information, of course, can be found in lots of different places. So the learning goal here for this section is to use electronegativity to determine the polarity of a bond, and then that's going to give us lots of information that we'll use later, all right? So first of all, electronegativity of an atom is defined as its ability to attract shared electrons in a chemical bond. The electronegativity of an atom is its ability to attract the shared electrons in a chemical bond. Now, it increases from left to right across the periodic table, and it decreases going down a group. It's high for nonmetals, where fluorine is the highest, and it's low for metals. Okay, let me go back to that graphic again now. You see that the highest of all of these is fluorine, okay? And the lowest is cesium, so it goes up in that direction. It goes up in that direction, okay? So this is really should be said. It increases in this direction, it decreases in that direction. It increases across here, increases that way, all right? So, and if you put those together, you can see that the highest is here and the lowest is here. Now, you might say, well, why doesn't helium have an electronegativity? And I would say, let's go back to the definition, the electronegativity is the capacity of an atom to attract shared electrons in a chemical bond. And helium doesn't make bonds, right? So these guys won't have any electronegativity at all because they don't make bonds. We're talking about the attraction of electrons in a bond. All right, so now that we know that, the difference of electronegativity can be appreciated in the following way. If you've got two hydrogen atoms and they share a pair of electrons, right? If they share them, they have the same electronegativity because of the same atom, right? Since they both are pulling on those shared electrons equally, then we would say that these electrons are shared equally and they don't go anywhere. So it's going to be a nonpolar, very equally distributed bond, okay? Now, if on the other hand you have a share between, see these two electrons get shared, hydrogen and chloride, and hydrogen was 2.1. What was the electronegativity of chloride? Electronegative chloride was what, 2.8? Let's go back and look at that table. No, chlorine is 3.0. You see it right there? Electronegativity is 3.0. And if it's 3.0, then that means, where was I here? That means that the difference is big, right? This is a bigger electronegativity than hydrogen does. And so since it's a big difference in electronegativity, then these electrons are actually not going to be shared equally. The one that is attracting them more is going to have them pulled over closer to that atom. All right? So this unequal sharing is going to make a partial positive charge here. That's what that little symbol right there means. It's a lowercase delta. It's a partial positive. That means that these hydrogen atoms are not really shared nicely. This hydrogen over here is saying, hey, I'm not getting my fair share. You electrons are getting pulled over by the chlorine atom, right? And chlorine is a bully, and it's got a partial negative. I covered up that symbol there. See that partial negative right there? That partial negative. So chlorine is actually getting more than its fair share because it's an electron hog. All right. So now nonpolar covalent bonds occur between nonmetals typically. Always between nonmetals. It is an equal or almost equal sharing of electrons by the two bonding atoms. Okay, and that's going to arise from a very small difference in electronegativity between the two. So if, for example, two nitrogen atoms are sharing electrons, well, their electronegativities are the same, 3 and 3, right? And so that difference is 0. So it's going to be nonpolar covalent. It's going to be shared evenly. Okay? If chlorine and bromine are sharing, their electronegativities are almost the same, right? Their difference is only 0.2. And so we're going to say, well, since they're so close to the same, it's basically shared evenly. It's nonpolar covalent. Hydrogen and silicon are almost the same. There's hydrogen's electronegativity, and there's silicon's, right? And so the difference is pretty small, and we're going to say, therefore, it's nonpolar covalent. So if it's anywhere between 0 and 0.4, we're going to say it's a small difference in electronegativity, and those atoms are equally pulling on the bonding electrons. However, if you have a big difference, then we're going to say, no, they're not being shared evenly. We're going to call it a polar covalent bond between two nonmetal atoms. That is an unequal sharing of the bonding electrons. And this has a difference. And we're going to say a moderate difference, not a small difference now, from 0.5 to 1.8, right? So let's look at some examples. The electronegativity of oxygen is 3.5. The electronegativity of chlorine is 3.0. And so the difference is 0.5, right, which is between 0.5 and 1.8. And so we're going to say, okay, they're not being shared evenly. It's polar covalent, okay? Chlorine and carbon. Chlorine is 3. Carbon is 2.5. The difference is 0.5, right? And so we're going to say, all right, well, that is polar then, right? Because the electrons are not being shared evenly. Oxygen and sulfur, 3.5 and 2.5. And the difference is 1, right? So oxygen's definitely pulling harder because oxygen's got an electronegativity of 3.5, right? So we're going to say that that's a polar covalent bond. All right, now since we have polar covalent bonds, we're going to represent those with little charges like that. We're going to say oxygen has a greater electronegativity. I happen to remember this one. Oxygen is 3.5 and carbon is 2.5, right? And the difference is 1. So oxygen's pulling on these electrons more. These electrons right here are getting pulled in this direction. And so we write it like this. We write an arrow with a plus sign next to the one that's less electronegative, right? You see that plus right there? We write an arrow with a plus sign by the atom that doesn't have its fair share of electrons, right? And the arrow goes toward the atom that's pulling harder. So we call this a polar covalent bond, and this is how we represent it. We say a partial positive and a partial negative, partial positive and a partial negative, right? Where the negative is the atom that has a higher electronegativity, right? The positive and negative ends of the dipole are located by using the lowercase Greek delta with a positive or negative charge and an arrow that points from the positive to the negative end of the dipole. All right, now what happens if the electronegativity difference is greater than 1.8? Okay, if it's greater than 1.8, then all of a sudden, this atom here, which has a higher electronegativity, just says, you know what, I'm going to steal your electron. I'm going to take it, right? We dealt with this in chapter 4 when we talked about, at the beginning of chapter 6 when we were talking about ions, right? And the reason why metals give up their ions is because they have a low electronegativity. So 0.8 and 3.0, wow, that's a big difference in electronegativity right there, 2.2. And so the chlorine is just going to steal it, and it's going to become Cl-, right? And leaves potassium crying for lack of its electrons in its wake. Broken-hearted, empty-handed potassium. I'm not sure if I said that right. There's my potassium right there. Broken-hearted and empty-handed. And it is therefore going to make an ionic bond, right? Same thing with nitrogen and sodium. Sodium's a metal, so it has a low electronegativity. We look it up in the table. We find it 0.9. We look up nitrogens, we find it's 3.0, and wow, that's a big difference, 2.1. Big difference in electronegativities. That's greater than 1.8. If it's greater than 1.8, which 2.1 is, then it's going to be ionic. All right, so in summary, the differences in electronegativity values for two atoms can be used to predict the type of chemical bond. If the electronegativity difference is between 0 and 0.4, we say it's small. That's a small difference, and we're going to say, therefore, it is nonpolar. If it's between 0.5 and 1.8, then we say that's moderate, right? That's not really a small difference. And we're going to say that bond is going to be polar, but still shared, okay? If it's greater than 1.8, then we say, you know what? It's not even shared anymore. It's ionic. and the electrons are considered to be stolen. All right, so between 1.8 and 2.0, we might either say it's sort of a gray area. Polar, covalent, or ionic, it depends on the elements involved. If a metal, and this depends on ionization energies, if it's a metal and a non-metal, then we say it's ionic. If it's two non-metals, we say it's covalent. All right, so this is sort of a fuzzy area between 1.8 and 2.0. All right, here's a picture, and I think a nice way to think of it. If you've got the electron cloud around two shared electrons, around two shared atoms, not two shared atoms, two electrons are being shared, right? You've got these two atoms, and they're sharing electrons, and here's the electron cloud in purple. Then we would say, oh, it's being shared evenly. It's nonpolar covalent. They're being shared equally, okay? And if this is exactly equal, then it's probably electronegativity difference of 0. But anything between 0 and 0.4 is going to be relatively even, right? Now, if you have one atom that's really pulling the electrons more, then the electron cloud is going to be bigger on this end, right? And see, since the electron cloud is bigger on this end, we're going to say it's partial negative. It doesn't have quite a full negative charge, but it feels a little negative, right? And that leaves this atom over here feeling a little lonely, a little naked from electrons, right? So it leaves a partial positive in its wake. Now, if it's a big enough difference, then we say this atom over here, it just steals it, and so it gets the charge. It steals the extra electron, and it leaves this atom without, and consequently with a plus charge. Okay, so predicting bonds. Here's table 6. I'm not going to go over this table. It's in your textbook. It just helps you practice sort of summarizes what we've already talked about. Let's do a learning check, and then we'll be done. Okay? Use the electronegativity difference to identify the type. So pause this video, and then make notes here, and then compare your notes to mine. Okay, so I'm going to suppose that you did pause it. I'm going to go look up the electronegativities of these guys, okay? The electronegativity of chlorine and chlorine, I remember that, but I'm going to look them all up. I'm going to pretend like I don't remember. I'm going to come up here. Potassium is 0.8. There's potassium right there. .8, and nitrogen is, let me come back here. Nitrogen is here. It's 3.0. Right? We knew this was going to be big, though, because it's a metal, right? Potassium is a metal. So 3.0, right? And it's really the absolute value. It's the difference we care about. So I'm going to say the absolute value. This is going to be a difference of 2.2, which is big, right? So we're going to say this is ionic. Okay? Let's do a different color here. Nitrogen, I just looked that up. It's 3.0 minus oxygen is 3.5, right? You see that there? Oxygen's 3.5. And it's the difference we care about. And that difference is 0.5, okay? And so we're going to say this is polar, right? Now, chlorine, whatever chlorine is, let's say it's X, it's also going to be X, right? Whatever that is, the difference is, of course, 0. And so this is going to be nonpolar, okay? And hydrogen is, some of these I have memorized, but I'm looking over here for you just in case. Hydrogen is 2.1, right? 2.1. And chlorine was 3.0. It's right over here, okay? 3.0. Right, and that difference is 0.9. And so that is going to be polar, right? All right, so I hope that's helpful. We're going to practice this with our homework. And I encourage you to familiarize yourself with the trends, but don't memorize it. It's not worth it. Good luck.